Good afternoon, guys. Sir DV again here to discuss to you the SOR method or the successive over relaxation technique, which is a variant of the Gaussseidel iterative technique. So the SOR technique is a method used uh, which aims to speed up the convergence by adding and subtracting a weighted value in the current iteration. And the formulation, of course, has to start with the Gauss-Seidel equation, in which the formula, as presented here in this lecture, is simply a generalization of the equation we have put into detail on my last lecture. So, which is this one here? Okay. So you will notice that that a term inside a parenthesis which involves a summation series exclude one term where the J subscript is not equal, or rather the J subscript is equal to the I subscript, meaning to say the term here which is included in the summation series, uh, specifically the A11 over A11 term x1, okay, was actually an exclusion of the summation formula. And so with the uh, A22 over A22 x2 term here is also excluded, and the A33 over A33 x3 here is also excluded. So in the SOR formula, we're going to retain this AII over AII xi term. So this will be retained, this 3 here, which represents the expression AII over AII xi, will simply be retained and multiplied into a factor W or omega to relax the iterate and expect a faster convergence later. Okay? But since we want the equation to be stable, if we retain this expression, we ought to subtract the same expression within the equation and hope for a faster convergence. So what are we going to do here now on this equation is to add, okay, or since this is a negative sign here, is to subtract a value AII over AII xi. Or we can also refer I, since I is equal to j, this can also be equal to xj. This is the term involving the series of the summation where j is equal to I. And of course, this is just equal to 1. And to make such expression the same, we have to add initially a value of xj here, but this xj must capture the latest iterate, k plus 1. So when I say k and k plus 1, I'm referring here to the cycle of iteration. Okay, it's the cycle or the number of iterate. So it refers to the first, second, third, fourth, fifth. So if I have two iterates involved here, k plus 1 and k, so I simply refer to the latest iteration in terms of k plus 1 and the older iteration in terms of k. So the two successive iterations now involves an old iterate k and a new iterate k plus 1. Okay, so if I do this addition and subtraction of xj here, I actually did not change the entire equation, except for the fact that the value of my iterate might not be the same, and so the relaxation procedure is now effective, no? So the latest iterate can come up with an expectation of finding, okay, as can be seen in this case, your second iterate k plus 1 on this second iteration uses your old iterate on the first two expression, but your new iterate on the first and the old iterate at the second on the second expression, and on the third expression we are now using both iterates. So the thing here is that we have to ensure that this expression here will involve an iterate or a solution vector which is an older, okay, expression, and while this ensures that these two here will ensure the latest iterate. So if we just do this thing here, we are going back simply into the Gaussseidel approach, and things will not actually speed up in terms of convergence. That's why we need to find a way on how to use the latest update in our program so that we can efficiently um, make the relaxation procedure worked. Okay, so but before we deal with such a scenario, we'd like to understand first and check if the program we are doing is just a refinement or a variant of the Gauss-Seidel approach. Hence, we first use the old, okay, formulation that I use on the last presentation, wherein in the Gauss-Seidel approach, I actually made use of the summation aij over aii from j equals 1 to n provided I have an if condition that j is not equal to 1. So this is the conditional statement that makes my Gaussseidel work within the limits of using the latest or the updated value of your x's. And in the relaxation, we simply uh, add, okay, we simply uh, use a weight w here and add this expression, which is actually a part of the summation j equals 1 to n of aij over aii xj without any restriction of the j not equal to 1 condition. Okay? So let's try to use the relaxation procedure first in the context of how the Gauss-Seidel works so that our program can be checked uh, and later be updated to fit the objective of speeding up convergence. So take note that when omega or w is equal to 1, this is a simple Gauss-Seidel iteration. When omega is less than 1, it is an under relaxation procedure. If omega is greater than 1, it is an over relaxation procedure. The word successive here simply states that we are doing it cycle by cycle. And take note of the range in which your W is used from 0 to 2 according to the book. So this is according to the lecture that we can use this range if we want to avoid divergence of the solution vector. So this of course must be checked out by you since relaxation procedure depends on values or depends on the system of equations involved and the property of the matrix. So we ought to check this range if really divergence will only take effect beyond those values. Okay, so let's go back to the original equation and try to use now my program, okay, using the relaxation equation or the relaxation method, assuming omega is equal to 1. And you will notice that the equation or the solution vector yields the same result with that of the Gauss-Seidel because I plug in omega is equal to 1. So as an exercise, I left this to the students to substitute a value less than or greater than 1 and observe how the convergence will take place by changing the value of omega. Notice that the number of iteration involved is the same, 6 iteration, coming up with your exact solution because this relaxation procedure, assuming omega is equal to 1, is simply a Gauss-Seidel iteration. Okay, so how to do it using the real relaxation method? So we ought to choose a value of xj which is relaxed or changed or modified by simply changing, no? Changing the value of omega or W to less than 1 or greater than 1, and try to observe what happens uh, to the speed of convergence. So thank you very much for listening. I hope you have learned and you have discerned how the SOR technique works by simply understanding the Gaussseidel principle on uh, this iterative procedure. I'll see you on the next video.